Primary function performed by the analysis phase is building of the symbol table. The location counter is a pointer that always contains the address of the next instruction to be executed. Look up and validate operation codes. That is to look up and validate the opcodes. Hello everyone, it is Dr. Ravikumar YB. Today we shall see the details of two-pass assembler. That is, in the previous classes, I was discussing about the design of two-pass assemblers. Moving ahead, we shall also learn about as to how we can fill the opcode table data structure and the symbol table data structure using the two-pass assemblers. That is, in case of two-pass assemblers, we will come across different types of data structures as well as the pointers which points to the address of an instructions. That is, in all these cases, we require a data structure called symbol table and opcode table, where the opcode table and symbol table are used in the first phase of the assembly language translation, and symbol table alone is used in the second pass of the assembly language translation. So let us see into the details of that as to how we can fill in those data structures and make use of it during the translation of assembly level language instructions to its equivalent machine language instructions. In this case, you will see that the primary function performed by the analysis phase is building of the symbol table. This is very, very important in case of analysis phase. When does the analysis phase begins? The analysis phase begins during the pass 1 of an assembly language translation. During this phase, whichever the opcodes and symbols we have been using in the programs are going to be parsed and analyzed. Once it is analyzed successfully, it has to be filled into the symbol table as well as the opcode table. That is during the analysis phase. That is also called as a pass 1 of an assembly language translation. What about the pass 2 of an assembly language translation? Yes, of course. Pass 2 of an assembly language translation is also an important language translation technique wherein you will see that the assembly language codes, that means the opcodes, also called as operand codes, used in that, also called as mnemonics. These mnemonics must be translated into its equivalent machine language format. That is to the numeric machine language format. If that is the case, we shall see as to how we can build the opcode table as well as the machine code table. And symbol table. In case of opcode table, we will be having two fields. One is the operand, that is the opcodes used. Then the other one is addresses. Similarly, in case of symbol table, we will have symbols used and the address corresponding to those symbols. Now, in this case, we have the opcodes. Now, for this purpose, it must determine the addresses with which the symbol names used in a program are associated. That means the symbols associated with their addresses must be determined. Sometimes it is not at all possible during the first phase of this. And of course, it is possible towards the end of an analysis phase. That is during the pass 1 of the assembly language translation. But not intermittently or in the middle of the execution of a program. It is not at all possible because there is a possibility of having the forward references. What is the meaning of forward references? As I have already discussed with you all, suppose if there is any symbol present in a program, the address associated with that symbol may be available at a forward information, may be available in future. But we have not yet encountered the symbol which is defined in the program. So without getting the definition of the symbol, it is highly impossible to get the address of those symbols used in a program. In such cases, we have to mark that as a blank addresses of those symbols in a symbol table. This enables us to fill up those addresses in the symbol table with the symbols associated with it at the later point of time. That is called as forward reference resolution. That is done in this case. Now, it is possible to determine some address directly. Example, the address of the first instruction in the program. However, others must be inferred. That means the address of the first instruction is by default known to all. For example, if there is a program name called John, the name of that begins with the start. Start is another opcode where that determines the beginning of the program. Always begins from the first address location. That is called as, by default, the address of that program begins from the default location which is there in the memory. Now, if that is the case, functions of assembler also includes the implementation of memory allocation in a data structure called location counter. Here I am using one more word here called location counter. This is very, very important. In short, I will call it as LC. This location counter enables you to determine the address of a next instruction to be executed. What is the meaning of that? Let me see that. Suppose if there are statement 1, 2, 3, 4, 5. When you are executing at this statement, in case of sequential execution of program, when you are executing presently, it points to the next instruction in this. That is this. Location counter points to this. When you are executing this, location counter points to this. So, when you are in the fourth instruction, location counter points to fifth instruction. When you are in the fifth instruction, location counter points to next instruction which is in sequence. That is when it is in the sequential execution of a program. Suppose if there is any jump statement present in it. Suppose if there is any definition defined inside a program, then it has to be jumped or invoked by calling the function definition from the calling function. That means R sub return to subroutine, jump subroutine, J sub jump to that subroutine, R sub return from subroutine. These are another type of opcodes. These opcodes are used when you have a program with definitions. In such cases, suppose if you have 1, 2, 3, 4. 4 instructions are there. You have a JSub function here. Opcode here, label here. Now it has to jump from here to the function definition which is defined here, that is 12, 13, 14, 15, 16. This is called as JSub function defined here, JSub here. R sub, what about the R sub? R sub. What is that? R sub indicates the return from here to here, that is from here to 5th, 6th, 7th, 8th, 10th, 11th, so on like that. When there is a J sub encountered, it has to, when it is executing the third instruction, the location counter points to J sub. When the J sub is encountered, when you are executing the fourth statement, there is a J sub that indicates that the control has to jump from here to this location. So location counter points to here. When you are executing in the fourth instruction, location counter moves to this 12th instruction and executes. Then execution comes here, starts executing. LC points to this location counter. When you are executing, when you execute this statement, that is statement number 15, location counter points to this. When you come to this point, that is this point of execution, location counter already moves to the 5th location, that is LC. It comes here. So that indicates that the location counter is a pointer that always contains the address of the next instruction to be executed, which needs to be executed by the program assembler. In this case, we have this location counter at this point of location. Then immediately when the control jumps from here to here, location counter points to the next. So this kind of process will begin until the execution of the entire program completes successfully. That is what stated here. It is initialized to the constant value. Then the location counter contains the address of the next memory word in the target program. Now, initialized to the constant value. What is that? Location counter. LC is initialized to 0, 0. Initially it is initialized to 0, 0. Whenever the analysis phase sees a label in the assembly statement, it enters the label and contents of LC in a new entry of the symbol table. That is, if you have any labels like this, immediately it comes to here, label L1, label L2, label L3, and correspondingly keeps the addresses initialized to blank in case of SIC architecture. In case of SIC XE architecture, that is in case of SIC architecture, these are initialized with blank. In case of SIC XE architecture, these symbols are filled with 0. L1, L2, L3, these symbols are initialized with 0. That is how the symbol table is defined and initialized initially. Later on, during the execution of the program, these addresses are filled with the actual address of those labels defined in a program. Next, location counter in a new entry of the symbol table. So in the symbol table, the values are entered, and when the second pass of a translation encounters, these symbol tables are made use of that. Then the translation of the code, intermediate files into the machine equivalent code is completed successfully with the help of this symbol table in the pass 2. Next. It then finds the number of memory words required by the assembly statement and updates. The number of memory words required for this execution of the entire program is encountered or tracked by whom? Location counter. Then that is the LC contents. This ensures that location points to the memory word in the target program. Even when machine instructions have different lengths and data space or data counts, statements are reserved different amounts of memory. Different amounts of memory is allocated because some words may require some definitions, or subroutines may require more space. Some subroutines may require less space. All those detailed informations are available with location counter. So this location counter is responsible for allocating the memory words in a memory locations with respect to the program defined. Now, to update this location counter, analysis phase needs to know lengths of different instructions. The same thing. Suppose if the instruction, what is the length of an instruction? That has to be determined by the location counter during the phase of analysis, that is, during the phase of pass 1. This information simply depends on the assembly language used. Hence, the mnemonics table can be extended to include this information in a new field called length. Now, in this case, we have mnemonics. When we come across the mnemonics, in the case of opcodes, again, opcode table is a data structure that contains the information which needs to be extended during the phase of analysis, that is, during the pass 1. We refer to the processing involved in the maintaining the location counter as LC processing. Next, the simple assembler with two internal data structure table called optab and simtab is used. Optab contains the informations like LDA, STL, and all those things are opcodes which we have used in our program. So such informations are stored along with their mnemonic values, that is numeric values. LDA as the equivalent 0, 0, 0, 0. STL as 14. So I can't keep this LDA, STL as it is in the machine language program. Everything must be converted into its equivalent zeros and ones. So an label or an operand, opcode, operand, 3 columns are there. Suppose here I will use L1, L2, L3. Somewhere in the opcode I will use LDA, R1, 100, STL, R1, L1 or L2. In this case, I have a label called L2 which is referenced later. So this is called as forward references. I am storing the value 100 into the register R1, and register R1 is used to store it into the label L1, L2. The L2 contains the storing of values here. So all these are certain type of information. These opcodes cannot be kept as it is in the machine language instruction. That has to be converted into its equivalent machine language instructions, that is LDA is equal to 0, 0, 0, STL is equal to 14. So these must be considered there. Again in the phase 2, that is during the pass 2, these values are mapped into its equivalent hexadecimal value, that is 14. What is the equivalent form of that? 0E. It is converted into this format, 0E. STL R1, L2. What is that R1? Again, R1 is a register operand that is considered into its equivalent. What is the label L2? What is the address present in it? Maybe 06. So this is how this part corresponds to the opcode table information. This corresponds to the symbol table. Together this corresponds to the word, one word. What is that one word indicates? As I have already discussed in the first session, that is one word is equal to how many bits? That is 1 byte is equal to 8 bits. So 8 bits into 2, that is equal to 16 bits. into plus one more 8 bits are added. 8 3s are 24. 24 bits are called as one word. That is, one word is equal to 24 bits. So here, how many bits are there here? 1, 2, 3, 4. So totally we have 24 bits to represent this information. So if that is the case, 0 can be represented as 0, 0, 0, 0. E can be represented as 14. 14E can be represented as this format. I convert this into an equivalent binary format. What is the binary format of E? E is equal to 14. 8421 code. 8421 code. 0, 0, not 0, 0. It is 1, 1, 1, 0. That has to be 1, 1, 1, 0. E, this corresponds to E. 0 corresponds to this. This 0 corresponds to this. This 6 corresponds to 4, 2, 1. So totally we have 8, 8, 16. Two more bits, two more information is to be required. That is this at the end. So this can be represented as 4 more bits, 0. And this 0 can be represented as 0. So totally this corresponds to one word. So this entire word is considered here. So we have an equivalent machine instruction format. This is the actual information we wrote in the assembly language. But what is the equivalent form of this? This is the equivalent form of this machine instruction. So this is how the information from the assembly language to the machine understandable format is converted. Now, let me move on to the next slide. The opcode table, also called as OpTab, contains the mnemonic operation and its machine language equivalents at least. The same thing as I explained here, LDA corresponds to 0, machine language mnemonic form. STL corresponds to 14, numeric information of a mnemonic. This is the numeric information of a mnemonic LDA. Numeric information of mnemonic STL. So these kind of informations are stored here. And then it contains the format and length. What is the format of this? This is the load format. This is for store format. This is how it is formed. During the pass one, OpTab is used to look up and validate operation codes. That is to look up and validate the opcodes that is present in the data structure table opcode tab, also called as OpTab. During the pass 2, OpTab is used to translate the operation codes to machine language. That is, especially during the pass 1, OpTab and SimTab is used. That is during the pass 1. During the pass 2, SimTab is used. SimTab is used. The same thing is used here. This in SIC-XC assembler, OpTab in pass 1 to find the instruction length for incrementing the location counter, LOCCTR. Next, organize a hash table, which is also called as a static table. Then SimTab. This is how the SimTab is followed. This is the name of the program, begins with the address 1000. First is the first instruction. Instruction 1 begins at an address 1000. C loop. Where is that C loop? It is defined here. It is at 1003. Then we have, when 1003 is encountered, we have a C loop here, then end fill. We have another thing. End of function. This is 3, 0, return address, length, buffer, read record. All these are certain information of opcodes with symbols, with these symbols used in the program. and built during the pass 1 and used in pass 2 of translation. Now, contains the type and length. Pass 1 labels are entered into the sim tab. That is, during the pass 1 is used, programs are built during the pass 1. That is, during the pass 1 labels are entered into the sim tab along with the assigned addresses, symbols along with their addresses. During the pass 2, symbols are used as operands and look up in the sim tab to obtain the addresses. That is, the symbols are used in the pass 2 of the translation. Next, organize a hash table, which is a static table. The entries are rarely deleted from the table. These entries are rarely deleted from the table. This assembler tables and location counter includes the logic like pass 1 usually writes the intermediate files. These intermediate files are used in the second pass, contains the source statement together with its assigned addresses, error indicators. That is, this with this addresses and error indicators. This file is used as pass 2. That is, these intermediate files are used in pass 2. Then format with fields like label, opcode and operand. That is the same thing which I explained earlier. That is this labels, opcode and operand. The same thing is followed here. Then example, this is the operand I am using. Suppose if I use the operand called RDREC. What is the meaning of RDREC? RDREC is a symbol that corresponds to read record. So we require a read record RDREC to read any subroutine which is present in a program. Then we have the assembler machine dependent assembler features like indirect addressing, immediate operands addressing, base relative addressing, then extended format addressing. In this case of indirect addressing, we will use the address through the index of that. That is, instead, if this is the location, this is the address of this, 1000 is the address of this. What is the value present in it? 25 is the value present in it. Instead of directly accessing the value 25, I will say that the value 25 is present at this location. Kindly go to this address, you will get the value 25. That is the term we use in case of indirect addressing. In case of immediate addressing, prefix directly we use, that is in case of operand LDA R1, 100. What is that 100? 100 is a constant or a literal which is assigned to a register R1. So directly we are using that. This is called as an immediate addressing. This is called as an immediate addressing. Always the operands begin with the hash symbol. That is, the symbols or literals are indicated by these hash symbol. Then base relative addressing. In case of base relative addressing, assembler directive base is used. Next, an extended format. In case of this extended format, adding the prefix plus to opcode. That is in XE, SIC, XE, we have the prefix plus to the opcode always. That indicates that the program is in this format. Then the use of register instructions is also possible. Instead of this R1 LDA R1, #100. Now I will use str store R1, R2. So register operations are happening here. So R1 to R2, the value is stored. So STL corresponds to R1 to R2. Then faster and don't require another memory reference. That is similar to the one which we have already obtained in the SIC format. In the SIC format, what we do? LDA R1, 100. STL R1, L1. That is called as label operations. Memory operations are required in case of this SIC format, but that is not the case with SIC XE format. That is, we can perform the register to register operations. That is LDA R1, 100 STL R1, R2. So directly we are transferring the contents of this from R1 to R2. That is loading this from 100 to R1 and R1 to R2. So that is what happening here in case of this. The same thing is stored here. Thank you very much. Let us discuss the same concept with continuation in the next session. If you have any questions, you can come to us online during the live session. Let me clarify all of your questions, all of your doubts, whatever the doubts you have in system software or in any of the subjects. Thank you very much. Thank you all.